The learning objectives of this topic include domain and range of a function, composite functions, one-to-one functions, inverse functions, sketching graphs of simple functions including piecewise defined functions, factor theorem and the remainder theorem, polynomial and rational equations and inequalities, decompose a rational expression into partial fractions, and a prime quadratic vector. These are the real-life applications and the importance of function in our real life and daily life, which relates to the economics and business modeling, logistic and network optimization, architecture, machine learning, and telecommunication.
Okay, function. So first, function fundamental introduce basic concepts such as domain, range, relations, one-to-one function, inverse function, and composite function. Next, graphing function focus on identifying and sketching different graphs including linear, quadratic, cubic, reciprocal, modulus, and piecewise function. For polynomial function, students will learn about polynomial degrees, the remainder theorem, and the factor theorem. The inequality section explain inequality symbol, nonlinear inequalities using sign diagram, and absolute value. Lastly, rational function and partial fraction covers rational function, proper and improper fraction, and partial fraction decomposition. Overall, this courseware helps students understand functions step by step, from basic concept to graphing and more advanced applications.
First and foremost, what is the function? Function is a special type of relation where every element in the domain is paired exactly with one element in the range. In a simple words, every input or x value has only one output or y value. Look at these two diagrams. Which one do you think is a valid function? Remember, the important rule is that every element in the domain has only one element in the range. So, the correct answer is both are function. As long as each element in the domain has only one output, it is still considered as a function. So, multiple x value can share the same y value, but one x value cannot have multiple y value. Now, let's move on to the concept of domain and range. The domain is the set of all possible input values, which is -2, 0, 3, and 11, while the range is the set of all possible of output values, which is -1, 5, 14, and 38. To find the domain and range in a graph, you can remember to look from the left to the right to find the domain, while look from the bottom to the top to find the range. Now, look at the curve. If the domain is horizontal and the range is vertical, where do the boundaries of the specific graph scratch? The curve expands infinitely outward horizontally, so the domain is all your number, while the range is y more than and equal to 0 because the graph starts from 0 and goes infinitely upward. Next, to determine whether the function is one-to-one, we can use a horizontal line test. If any horizontal line intersects the graph more than once, it is not a one-to-one function. But if every horizontal line only intersect in the graph only once, it is one-to-one function.
Now, let us look at composite functions. And a great way to picture them is like a processing line with two machines joined together. Imagine we drop an input x into our first machine, machine Gx. It processes x according to Gx equals to x plus 1 and outputs the result Gx. Immediately, that output feeds straight into machine Fx, where Fx equals to x power of 2. Let us trace it step by step. So, step 1, we substitute Gx inside Fx. It's giving us f in the bracket x plus 1. Step 2, applying the rule for f. We square the entire input, resulting in fg of x equals to x plus 1 power of 2. That's all a composite function is, passing an output from one function directly as the input into another. Now, on to inverse function. Before we jump straight to finding an inverse, we must ask a critical question. Does the function actually have an inverse? To have an inverse, a function must be a one-to-one function. We check this visually using the horizontal line test. On the left, look at fx equals to exponent power of x. Any horizontal line we draw crosses the graph at most once. This means the graph, it passes the test. It is a one-to-one function, so its inverse exists. On the right side, look at gx equals to x power of 2. If we draw a horizontal line across y equals to 4, it crosses the parabola twice at x equals to 2 and x equals to negative 2. Because it fails the horizontal test line, gx does not have an inverse over all real numbers unless we restricts its domains. Once we know an inverse exists, how do we find and visualize it? Graphically, an inverse function, f inverse of x, is a reflection of fx across the line y equals to x. Notice how the domain of f becomes the range of inverse of f, and vice versa. To calculate inverse of f algebraically, we follow a simple three-step algorithm. Set y equals to fx to write it as an equation. Swap x and y variables. This mirrors our reflection across y equals to x. Then, solve algebraic for y. The isolated y is your final inverse function, where f inverse of x. Finally, let us look at piecewise functions, specifically taking an example straight from specimen paper 2. Here, we have defined in fx into two distinct pieces depending on its domain. When sketching piecewise graph, boundary points are crucial. Closed circle with solid dots used at x equals to 1 for x plus 1 because the inequalities is greater than or equal to. And for the open circle, which is hollow dot, used at x equals to 1 because because the inequalities is strictly less than. The point 1, 0 is an exact boundary, but not included in this piece, keeping track of these boundaries and points and ensures that piecewise sketches are mathematically precise every single time.
Now, moving on to the quiz section. Quiz 1. Which of the following is graph represent y equal to 1 over x? Yes, the answer is A, which is the reciprocal function. How do we get the answer is A? Let's see the calculation. So the question is, we need to find the graph of y equal to 1 over x. So we need to find 2 points in order for us to sketch the graph. Step 1, we need to substitute any value of x. For example, we choose x equal to 1 and we get the y value is 1. So point 1 is 1, 1. Then we can plot the 1, 1 in the graph. Step 2, we choose any value of x. For example, x equal to negative 1. And we get the answer for y is negative 1. So point 2, we get negative 1, negative 1. So we sketch the negative point 2 at the graph. So the answer that close is the point A. Quiz 2. Which of the following is graph represent y equal to 2x minus 1? Yes, the correct answer is B. The concept is same from the previous question, which is we need to find 2 points to sketch the graph. So for the first, we substitute value of x into the equation and we get the value is for x is 0 and y is negative 1. So we plot in the graph. For the second step, we substitute the value of y into the equation and we get the output is 0.5 and 0. So we sketch 2 points into the graph and we get the answer is B. Moving on to the quiz 3, the question is, what is the domain and range for y equal to 1 over x? Correct, the answer is C, which is the domain and range is negative infinity to 0, union 0 to infinity. Or we can rewrite as a domain and range is all real number except 0, since the graph is not touches the x-axis and also y-axis. Next, quiz 4. What is the domain and range for y equal to 2x minus 1? So, the correct answer is D, which is the domain and range is all real numbers, or we can also denote it as negative infinity to infinity. Since 2x minus 1 is a linear function, there is no restriction for the value of domain and range. Therefore, the value of domain and range can be the all possible value of the input and also the output. Moving on to the quiz 5. What is the function for composite function f(g(x) given the function fx is 1 over x and gx is 2x minus 1? The correct answer is B. Function for f(g(x) is 1 over 2x minus 1. How do we get the composite function? First, we need to start with the outer function, which is fx equal to 1 over x. Second, we need to identify the inner function, which is gx equal to 2x minus 1. The third step is we substitute the gx function into the fx function, and finally we get the final answer for the composite function fgx equal to 1 over 2x minus 1. Moving on to the Geogebra demonstration for the previous question. There are two functions, which is fx equal to 1 over x and gx equal to 2x minus 1. Student can tick on the first text box to display the graph for fx and also gx. So the green graph display indicate that the graph for function fx equal to 1 over x, and the blue graph indicate that the graph for function gx equal to 2x minus 1. So the question A is to find the domain and range for both functions. So tick the first checkbox for the domain and range for the function fx. For fx equal to 1 over x, the denominator cannot be 0. Therefore, the domain and range is all real number except 0, or it can also be written as open round bracket negative infinity to 0, union open round bracket 0 to infinity. This indicates that the domain is all real number except 0. Next, for gx equal to 2x minus 1, this is a linear function. There are no restriction on the value of x, so the domain and range is all real number, or can be written as open round bracket negative infinity to infinity. For question B, find composite function fg and state its domain and range. Composite function fg is, we need to substitute gx into the function fx, and the answer is 1 over 2x minus 1. So when we click on the checkbox, it displays the red graph, which indicate the graph for the composite function. Next, to determine the domain for the composite function, the denominator must not be 0. So 2x minus 1 not equal to 0, which gives x not equal to 1 over 2. Therefore, the domain for function composite function fgx is all real number except x equal to 1 over 2. Finally, for the range, the output of 1 over 2x minus 1 can never be 0 because the numerator is always 1. Hence, the range is all real number except 0.
Alright everyone, let us take a look and put our knowledge to the test with question 6. What is the domain and range for the following equations? Fx equals to 1 over x and gx square root of x minus 1. This question asks us to identify the correct domain and range for these functions from our choices on the right. And the correct answer is E. Let us take a look into the calculation. Let us break down how we find the domain for both functions mathematically. First, for fx equals to 1 over x. Steps 1 and 2, a fraction is undefined when its denominator equals to 0. So, our key restriction is x cannot equal to 0. Step 3 and 4, this means x can be any real numbers except 0. Expressed in set notation, the domain is domain of f, real numbers, or x cannot equal to 0. Looking at the graph, you can see the curve splits right at the vertical asymptote, x equals to 0. Next, for gx equals to square root of x minus 1, step 1 and 2, for a square root to yield real numbers, the expression under the radical must be non-negative, which means equal to or more than 0. Step 3 and 4, which involving in solving the inequalities, where x minus 1 equals to or more than 0, gives us x more than and equals to 1. Therefore, the domain is domain G, x any real numbers, and x more than or equals to 1. As shown on the graph, the function begins precisely at x equals to 1 and extends to the right. Question 7. What are the inverse of the following equations? The correct answer for these questions is A. Now, let us walk through the full algebraic process of finding and verifying the inverse for both of our functions. First, let us look at function fx equals to 1 over x. Step 1. We express the functions as y equals to 1 over x. Step 2. Swap our variables to get x equals to 1 over y. Step 3. Rearrange to solve for y. By multiplying both sides by y gives xy equals to 1, which simplifies to y equals to 1 over x. Step 4. Replace y with inverse notation, giving f inverse of x equals to 1 over x, a self-inverse function. For the verification check, notice on the right of the left box, substituting f inverse x into fx yields f 1 over x equals to 1 over 1 over x, which equals to x. Likewise, inverse of f function of fx equals to x. Both yield the identity x, confirming our answer is 100% correct. Next, let us solve for gx equals to square root of x minus 1. Step 1. Write it as y equals to square root of x minus 1. Step 2. Swap x and y to obtain x equals to square root of y minus 1. Step 3. To isolate y, we square both sides to eliminate the square root, giving us x squared equals to y minus 1. Adding 1 to both sides gives us y equals to x squared plus 1. Step 4. State our result in the inverse notation as stated in the slides. Now let us test our understanding of graphing piecewise function with quiz 8. We are asked to select the correct graph for fx, x squared, and 2, which if x less than 0 and if x more and equals to 0. Let us analyze what each piece should look like before making our pick. For all values of x to the left of the y-axis, x less than 0, the graph should follow the parabola of x squared. For all values of x to the right of the y-axis, including x more or equals to 0, the graph should be a flat horizontal line at y2. to take a quick look at the choices A, B, C, and D. Which one matches both behaviors? And yes, you are correct. The answer is C. Okay, let us move on to the Geogebra demonstration. So, according to my previous slides or previous questions, we are using two functions, which is fx equals to 1 over x, and also gx equals to square root of x minus 1. This Geogebra demonstration will be focused on two questions, domain and range, and also inverse functions. Let us take a look on how to sketch the graph. So this is the graph for the function fx. This is the graph of function gx. So let me uncheck the checkbox first. Okay, the first checkbox is fx. So the domain and range of fx is stated over there. As you can see, the domain and range is a union of negative infinity 0 and 0 infinity. It cannot equals to 0. On to the function and the domain and range of function gx. The domain and range is 1 to infinity and 0 to infinity, where it was always more and equals to 0. Why? Because in the square root function, it cannot be a negative number. Okay, let us move on into the next questions involving inverse function. I'll use the invert functions in Geogebra to portray the answer and also the outcome for the graphs. As you can see, the inverse function of fx is 1 over x. Next, the inverse function of gx is x squared plus 1, which will indicate or will portray a quadratic graphs.
Okay, now I will present the topic entitled Steering Polynomial, the magic of remainder and factor theorems. In this presentation, I will explain what polynomial functions are, how polynomial divisions work, and how the remainder theorem and factor theorem help us solve polynomial problem more efficiently. Before we move into the deeper, we need to understand polynomial functions. A polynomial is an algebraic expression consisting of variable and constant with non-negative integer exponent. For example, look at the interactive degree board. The first one is degree 1, or we call it as linear, ax plus b, degree 2, quadratic, ax squared plus bx plus c, degree 3, cubic, ax cubed plus bx squared plus cx plus d, and the last one is degree 4, quartic, ax power of 4 plus bx cubed plus cx squared plus dx plus e. In general, a polynomial can be written as, so the degree of a polynomial is the highest exponent of the variable. The next concept is the function 0 or root of a polynomial. A value of x is called a 0 if substituting it into the polynomial makes the functions equal to 0. For example, given fx equal to x minus 2, x plus 1, and the last one is 2x plus 1. If you substitute x equal to 2, f2 becomes 0. If you substitute x equal to negative 1, f negative 1 becomes 0, and the last one, we substitute x equal to 1 over 2, f 1 over 2 becomes 0. Therefore, the 0 of functions are 2, negative 1, and the last one is 1 over 2. Now, let's look at the structural blueprint of polynomial divisions. Whenever a polynomial is divided by another polynomial, we obtain 4 parts. The first one is the dividend, where the original polynomial are divided. The divisor, where linear expression dividing the polynomial. The third one is the quotient, where the resulting polynomial answer. And the last one is the remainder, where what is left over, a constant if dividing by linear. So the relationship is fx equal to x minus a multiplied by qx plus r. This equation is very important because it becomes the basis of both the remainder theorem and the factor theorem. Traditionally, we find the remainder using polynomial long division. Although this method is accurate, it requires several steps and calculation. As we can see, we repeatedly divide, multiply, subtract, and bring down terms until the process is complete. Because this method can be time-consuming, mathematicians develop a much faster approach using the remainder theorem. So we can see the movie magic. Instead of performing long division, we only need to substitute the value of a into the polynomial. When we substitute a into x in the equation, it will become 0. And when 0 multiplied by qx also becomes 0, so the last reveal fx equal to r, which is fx equal to the remainder. So the remainder theorem states that if a polynomial f px is divided by x minus a, then the remainder is simply, we call it as PA. So this saves both time and effort, especially when dealing with the high degree polynomial. So now let's look at an example. Find the remainder when px equal to 3x power of 5 minus 2x cubed plus 7 is divided by x minus 2. So using the remainder theorem, we substitute 2 into the x and it will become 96 minus 16 plus 7, and therefore the remainder is 87. So we can get the answer, but we never needed to perform long division. Next, the factor theorem. The factor theorem is actually an extension of the remainder theorem. It states that if PA equal to 0, then x minus a is a factor of the polynomial. In other words, remainder equals 0 means divisor is a factor. But for the rule 1, if a polynomial px equal to x minus a, become the factor if and only if PA equal to 0. For the rule 2, for a polynomial px equal to ax minus p, become the factor if and only if b over a is 0. This theorem is very useful for factorizing polynomials and finding roots. So let's apply the factor theorem. Suppose x minus 1 and 3x plus 1 is a factor of equation fx equal to 3x cubed minus ax squared plus bx plus 2. Since x minus 1 is the one of the factor, so f1 becomes 0. We substitute x equal to 1, give for our first equation, and another factor is 3x plus 1. We get the x minus x equal to negative 1 over 3. So we substitute x equal to negative 1 over 3, and we get another equation. And the last one, the final cut, we substitute equation 1 and equation 2 that we get from the factor, and the last answer we get a equal to 8 and b equal to 3. Finally, we solve the simultaneous equation to find the unknown constants. This is much easier than we use the long division repeatedly. Now, let's compare the two theorems. The remainder theorem helps us determine the remainder after the division. Meanwhile, the factor theorem tells us whether the divisor is actually a factor. So the process is, first, you need to substitute the value into the polynomial. If the result is not 0, that value is the remainder. But if the result is 0, then the divisor is a factor. So as we can see, when we substitute 3 into the equation, we get 0. So it will become the factor theorem. But when we substitute 1, we get 24. So it will show us that it is a remainder theorem. So both theorems work together and make solving polynomial problem much faster. Last one, this is the table for comparison factor theorem and remainder theorem. So you can see the difference between both theorems.
Inequality. First, an inequality is similar to an equation because both compare to expression. However, an equation uses the equal sign while an inequality uses symbols such as less than, greater than, less than, or equal to, and greater than or equal to. For example, x less than 5 means that x can be any value smaller than 5. So to solve an inequality means to find all values of the variable that make the statement true. There are two common types. A linear inequality contains a variable with power 1, such as 2x plus 3 greater than 7. A non-linear inequality may contain products, fraction, or variable with higher power, such as x squared minus 4 less than 0. Next, there are several important rules. We may add or subtract the same number on both sides without changing the inequality sign. We may also multiply or divide both sides by a positive number. However, when we multiply or divide by a negative number, the inequality sign must be reversed. For example, if negative 2x greater than 6, dividing by negative 2 give x less than negative 3. For non-linear inequality, we first move all terms to one side so that the other side becomes 0. Then we factorize the expression and find the critical value by setting each factor equal to 0. This value divide the number line into several intervals. We test one value from each interval to determine whether the expression is positive or negative. Finally, we select the interval that satisfy the original inequality and check whether the endpoint should be included. The slide. Next, absolute value inequality. Absolute value represent the distance of a number from 0, so it is always non-negative. For example, modulus x less than 3 means that the distance between x and 0 is less than 3. Therefore, the solution is the solution is x greater than negative 3 less than 3. Meanwhile, modulus x greater than 3 means that x is more than 3 units away from 0. So x less than negative 3 or x greater than 3. Lastly, inequalities involving modulus can be solved in different way. We can apply the properties of modulus, square both sides when appropriate, or use a graph to identify the value where one expression is above or below, or use a graph to identify the values where one expression is above or below another. Overall, the topic teach us how. Overall, inequality teach us how to compare expression and find a range of possible value instead of finding only one exact answer. A rational function is a function written as a fraction. Okay, here nx is the numerator and the x is the denominator. Both are polynomial. The denominator cannot be 0 because division by 0 is undefined. There are two main types of rational function. A proper rational function occurs when the degree of the numerator is smaller than the degree of the denominator. An improper rational function occurs when the degree of the numerator is equal to or greater than the degree of the denominator. For an improper rational function, we normally use polynomial long division first. Next, we learn about partial fractions. Partial fraction decomposition means changing one complicated rational expression into a sum of simple fractions. These simple fractions are easier to calculate, integrate, or use in other mathematical problems. The form of the partial fraction depends on the factors in the denominator. For different linear factors, we use one simple fraction for each factor. For a repeated linear factor, we include fraction for every power of that factor. For an irreducible quadratic factor, the numerator must be written in the form ax plus b. After writing the correct form, we find the unknown constants such as a, b, and c by comparing coefficients or substituting suitable values of x. To solve a rational function problem, we first identify the numerator and denominator. Then we check whether the function is proper or improper. Next, we factorize the denominator completely and write the correct partial fraction form. After that, we determine the unknown constant for an improper function. Long division must be completed before decomposition. There are also several important reminders. Any value that makes the denominator 0 must be excluded from the domain. This value may also help us identify vertical asymptote. When sketching the graph, we should examine the intercept, asymptote, holes and general shape of the graph. Finally, we should check the answer by combining the partial fraction again to make sure they produce the original expression. Overall, rational function involve polynomial fraction, while partial fraction help us break a complicated fraction into simple and more manageable parts.
Okay, now the purpose of this quiz is to check your understanding of the lesson and reinforce the key concept you have learned. So for the quiz 1, given the polynomial px equal to 2x cubed minus 3x squared plus x plus 5. So for the question 1, find the remainder when px is divided by x minus 2. And the answer is A, 11. So now let's look for the calculation. For the calculation, first one, identify A and apply the remainder theorem. So for the remainder theorem, when px is divided by x minus a, the remainder is pa. So we are dividing by x minus 2. So our a is 2. Step 2, substitute x equal to 2 into px. And the step 3, evaluate the step by step until we get the last answer. We substitute, we multiply and add, and the last one, the conclusion, we have the final answer and we get 11. Therefore, the remainder when px is divided by x minus 2 is 11. Next, we move to the question 2. Find the remainder when px is divided by x plus 1. The answer is C, equal to negative 1. So, let's look for the calculation. For this question, we need to divide by x plus 1. So, a equal to negative 1. Step 2, substitute x equal to negative 1 into px. And step 3, evaluate step by step. And the last one, we have the conclusion. Therefore, the remainder when px is divided by x plus 1 is negative 1. For the third question, we have find the remainder when px is divided by x minus 1. And the answer is A, equal to 5. Okay, for the last question, question 3, we need to find the A and apply the remainder theorem. So, A equal to 1 because we are dividing by x minus 1. Step 2, substitute x equal to 1 into the px. And step 3, evaluate step by step involving substitute, multiply and addition. And so step 4, conclusion, we have the remainder equal to 5 when px is divided by x minus 1. So we move to the quiz 2. Given that x plus 2 is a factor of the polynomial px equal to 2x cubed minus x squared plus alpha x minus 6. So we need to determine the value of alpha. So the answer given A, negative 13, B, 13, C, negative 7, and the last one, D, is 7. And the answer for this question is A, negative 13. Let's jump into the calculation. Okay, so for this calculation, the first one, we need to use the factor theorem. If x plus 2 is a factor of px, then p, negative 2 equal to 0. Next, step 2, substitute x equal to 2 into the px. And the last one, step 3, we need to solve this question and until we get the alpha equal to negative 13. So the final answer we get is alpha equal to -13.
Okay, next, I will demonstrate on how to use this GeoGebra and function as a tool to verify whether our manual calculation are correct. So instead of calculating the remainder by the hand every time, GeoGebra help us to quickly check our answer using the remainder theorem. So for the quiz 1, we have the polynomial given px equal to 2x cubed minus 3x squared plus x plus 5. So we can see this graph for this polynomial on this side. And the blue vertical line represent the current value of a on the x-axis. As I move the slider, the value of a change and the blue line move left or right to the corresponding x coordinate. So for the question 1, we need to determine the remainder when px is divided by x minus 2. So according to the remainder theorem, the remainder is equal to PA, where the divisor is divided by x minus a. So since the divisor is x minus 2, the remainder will become P2. As we know, a equal to 2. So we move the slider to 2 and we get the answer PA equals to 11 or P2 equals to 11. Okay, next, we move to the question 2. Determine the remainder when Px is divided by x plus 1, which can be written as x minus 1, and the remainder will be P negative 1. So I will move to the negative 1, and we can see its current value of a is negative 1, and we get the PA equal to negative 1. So the remainder for the question 2 is negative 1. We can compare this value with our manual answer to verify that it is correct. So next, the last for this quiz, we need to determine the remainder when Px is divided by x minus 1. So the remainder will become P1. So I will move to the 1. A now we become to 1, and the value of PA is 5. So overall, the slider let us choose the value of A, while the blue vertical line show the position on the graph. GeoGebra can instantly calculate PA, making it a fast and effective way to check whether our manual calculation are correct.
Okay, so for the quiz 2, given that x plus 2 is a factor of the polynomial given, so the negative 2, p negative 2, we need to define it as p negative 2 equal to 0. So we need to find the value of alpha. So in this GeoGebra, we need to put the value in this input box. For example, we search the alpha is negative 13. So we need to click the enter, and yeah, our answer is correct, and the graph is shown given, and the PA negative 2 equal to 0. So our answer is correct, and therefore x plus 2 is a factor. If I put the wrong value, for example, I will put 12, and the answer is show the incorrect, and x plus 2 is not a factor. So this is GeoGebra help us to check the answer.
So in order to test the understanding of the students for the topic, students have to answer this quiz, okay, which is we'll sketch on the same coordinate x, the graph of y equal 2 minus x and y equal modulus 2 plus 1 over s. Hence, solve the inequality. Based on the equation y equal 2 minus x, determine which graph correctly represent the equation. So students have to choose which one the correct answer that represent the correct graph based on the equation, which is y equal 2 minus x. Okay, so student can choose between A, B, C and D. So the answer for the quiz is C. Okay, so this is for manual calculation. This slide show the step-by-step calculation for sketching the graph manually. Okay, so first we identify that this is a linear equation. So the graph will be a straight line. Okay, next we find the y-intercept by setting x equal to 0. Substitute in the equation, then we get y equal to 2. Then we find the x-intercept by setting y equal to 0. So substitute again into the equation. So we get x equal to 2. Therefore, the graph crosses the x-axis at 2, 0. After that, we determine the gradient, okay, by comparing the equation with the general form. The gradient is m equal to -1. Okay, a negative gradient means that the line slope downward from left to right. Okay, finally, we plot the two intercepts, 0, 2 and 2, 0, and draw a straight line through them. So the correct graph must cross the y-axis at 2, cross the x-axis at 2, and slope downward. Therefore, the correct answer is C. Okay, next, students have to answer about the based on the equation y equal modulus 2 plus 1 over x. Determine which graph correctly represent the equation. Same goes to the first question. Okay, so student have to choose correctly that represent the graph based on the equation between A, B, C and D. The answer for the question is C. This is manual calculation. How to get the graph. Okay, so first we remove the modulus by considering whether the expression inside it is positive or negative. Next, we find where the expression inside the modulus equal to 0. Okay, 2 plus 1 over x equal to 0. So 1 over x equal to -2. And therefore, x equal to -1 over 2. This means the graph touch the x-axis at -1 over 2, 0. Now, we determine the formula for each interval. Okay, therefore, y equal 2 plus 1 over x. Okay, there are several important features of the graph. The function is undefined when x equal to 0. So, the vertical asymptote is x equal to 0. As x become very large in the positive or negative direction, 1 over x approaches 0. Therefore, the horizontal asymptote is y equal to 2. Okay, because this function contains a modulus, all its y values must be 0 or positive. Any part of the original graph below the x-axis is reflected above it. Therefore, the correct graph has a vertical asymptote at x equal to 0, a horizontal asymptote at y equal to 2, and touches the x-axis at -1 over 2, 0. Hence, the correct answer is C. So, this is how to combine both graphs on the same coordinate x. This is how it looks like. The two graphs combined on the same coordinates x. Okay, next, student have to solve the inequality. Okay, student also can choose between A, B, C and D, the correct answer for the question. Okay, so the correct answer for the question is B. This is how to get the answer manually. So first we state the domain. Since 1 over x is undefined when x equal to 0, next notice the right hand side is an absolute value, so it is always greater than or equal to 0. Therefore, the left hand side must also be positive. Okay, 2 minus x greater than 0. Hence, x less than 2. Now we use the graph to find the point where the two expressions are equal. 2 minus x equal modulus 2 plus 1 over x. So we solve it and we get the answer x equal to 2 plus minus set 5. However, we already know that x less than 2. Therefore, 2 plus set 5 is not valid because it is greater than 2. The valid intersection value is x equal 2 minus set 5. Finally, we read the graph, the straight line. So in decimal form, x equal to -0.24. So all value smaller than approximately 0.24 satisfy the inequality, or else the solution is x less than 2 minus 5. Okay, so this is solution how to use the GeoGebra to solve the inequality by comparing two graphs, which is fx equal to 2 minus x and gx equal to modulus equal modulus 2 plus 1 over x. So first, student have to tick the checkbox beside the first function. Okay, so GeoGebra will display the blue straight line, okay, which is fx equal to 2 minus x. Then tick the checkbox beside the second function. So GeoGebra will display the green fractional graph. Okay, so gx equal to modulus 2 plus 1 over x. So the function gs is not defined at x equal to 0. So the green graph has a vertical asymptote at x equal to 0. Okay, next, take intersection of the graph. GeoGebra will show the point where the two graphs meet, which is p equal to negative 0.24, 2.24. Okay, so therefore the approximate intersection value is negative 0.24. Okay, so student can click the solution checkbox to display the calculation and final answer. And student also can see clearly about the graph. Okay, and then how the intersection point is happen between the two graphs, and the last one is the solution for the final answer. So that's it for the solution in GeoGebra.
In conclusion, this presentation has introduced the fundamental concept of function and highlighted their importance in solving mathematical and real-world problems. We explained the key concepts, including function, domain, range, one-to-one function, composite function, polynomial, rational equation, and inequalities before applying them to real-world application questions. Through the GeoGebra interactive worksheet, we demonstrate how technology can be used to visualize graph, analyze mathematical relationships, and verify solutions more efficiently. The interactive features of GeoGebra make it easier to determine domain and range, identify the correct graph, and understand the behavior of different types of functions. This not only improves accuracy but also enhances conceptual understanding and problem-solving skills. Overall, integrating GeoGebra into the learning process provides a more engaging and interactive approach to mathematics, helping students connect mathematical theories with practical application. We hope this presentation has provided a clearer understanding of function and demonstrate how digital tools can support effective mathematics learning. That's all from us. Thank you for your attention.